Hi, this is Colleen Quinlan. This is the first project using a simple majority predictor algorithm. It's a naive algorithm, so we are expecting relatively poor accuracy and high error. We were provided 6 training data sets, 3 of classification and 3 of regression. I'm going to walk through my code now. So I go ahead and you can run this. You click Choose Files. I'm gonna upload my data files only, as I've coded the names, files, information into the training algorithm. So you open those 3 files, you can see that they are saved to the error. We were provided 6 training data sets, 3 of classification and 3 of regression. I'm going to walk through my code now. So I go ahead and you can run this. You click Choose Files. I'm gonna upload my data files only, as I've coded the names, files, information into the training algorithm. So you open those 3 files, you can see that they are saved to the you can see I've uploaded the data a couple times because I've practiced. So I have hard-coded this because I did not get the configurable code working in time and I wanted to have data results. But if I had finished coding it, I would have used a dictionary with each of the training set names, which then could have been used to retrieve the column names, which would have then been applied to the data and used to organize it. So there would be more attributes and more. I've hard-coded the file name here again. If I'd used the dictionaries, I would loop through the dictionaries, probably all of the regression first and then all of the classification. I would look up the names in the dictionary instead of hard-coding them here. You can see I've added 3 columns. This is for the sex attribute because the attribute is nominal and it needs to be an integer. And so because it's not an ordered attribute, we use hot encoding to encode it properly. So then we read the CSV into a data frame. And then here we have the hot encoding. And so if I had done this as a configurable file, this would be a function and it would receive the new column names and then the original column name, and then it would be done configurably. Here we have the z-score calculation, and so this is just creating the function for it, which is then called later. Here we have the mean squared error function. We take results and test data as our input, and then k, which is our number of buckets. I'll run this as well. So this is our cross-validation. You pass in the data. K is the number of buckets. This is initializing the result array. This fractional test is the percentage of data that you want to reserve for testing. Shuffling randomizes our data sample. This is establishing the k buckets of equal data distribution. Again, we reserve 20% for testing, so we go ahead and set aside that test data here. We remove the test data from the training data. We take the mean of the ring values in the training data, and then we store that in a result set array. And then we increment the loop. We call the mean squared error function using the trained results and the test data that we had reserved, and then the number of buckets. That calls the code that we discussed earlier. And then we call the z-score using the training data and the test data, and that normalizes using z-score normalization. If we were to use this, I think that this normalized data is what you would pass into a model. So I go ahead and call the cross-validation function here. I've printed the mean score error for each of my 5k subsets. You can see it's relatively stable. And then I have modeled the z-score normalization for each of those attributes. And you can see that the MFI probably does not make sense to normalize or to attempt because you know, it's either 1 or 0, so it's a binary value. And you can see here that those are the ones that really aren't normalized. So were we to continue coding this, we would remove these 3 columns